Okay, good morning. So we've been talking about the basically the atoms, right? Just gas phase atoms. We looked at the wave functions of the atomic orbitals. We came up with electron configurations. We looked at the data supporting those, and we supported the idea that half-filled subshells are stable and so on using the ionization energies, which required us to do electron configurations of cations and so on. And then we got into the term symbols, which required us to do, with the Grotrian diagrams, electron configurations of excited states. So we saw that a single atom can have dozens of electron configurations because you can put that electron cloud together in many different ways. So now we're getting to the Grotrian diagram, the changes between the energy levels. We have spectral lines. So now we're able to do atomic spectroscopy. So we could do atomic spectroscopy as the analytical chemist does it, okay, which in that case is basically Beer's law. So if you go over to TRI's, they have quite a few atomic spectroscopy instruments. I think in instrumental we do atomic absorption using a little nebulizer and a flame. Have y'all seen any of that? Yeah, so you do flame AA, flame atomic absorption. But as a physical chemist, I mean, it's Beer's law, right? A equals EBC, ABC. You know, it's pretty simple stuff. You have the molar absorptivity, the path length, and the concentration. It's not a lot of like meat there. So I'm not so interested in that. When I discovered that you could do spectroscopy on stars millions of light years away, I thought, now wait a second. That's really much more cool than Beer's law. Okay, so we could do a whole lecture on Beer's law on atomic absorption, but you're going to get that in analytical chemistry. So I don't want you to think, though, that atomic spectroscopy is the only thing we use. Atomic spectroscopy for stars is the only use for atomic spectroscopy. It's very useful in analytical chemistry, but you're going to get that in instrumental analysis, and it's Beer's law. Okay, so let's look at how we can apply atomic spectroscopy to the stars out there in the universe without ever having to leave Earth. That's pretty neat. Okay, so stellar spectroscopy and the expanding universe is this lecture. So they found this out many years ago, that once they developed the Bunsen spectrometer, they could, instead of using a light source like a gas discharge bulb, they could aim this at the sun and they could look at the rainbow that comes out. So they aimed the spectrometer at the sun, exposed some film, they saw, the rainbow, if you will. They didn't really have color film back in the day, but they could see that it was brighter in the middle than it was at the outside. And this was the same sort of general envelope of lines that they got from a black body. So remember, the very first lecture we talked about was black body radiation, and it was a function of temperature, so they could get a feel for how hot the sun was. And they saw that it was extremely hot, at least the outer part of the sun. It was giving this profile of like 6,500 Kelvin. So it would match a hot object, like if you heated up a piece of metal up to 6,500 Kelvin, it would be white hot. And it would look like this broad emission that we get from the sun. But when they got more resolution, they narrowed the slits, they could see some dark lines. And so these right here are called the Fraunhofer lines. They're dark lines in the spectrum. And notice how thin they are right here. These are really sharp lines. And we know from the Grotrian diagram and the atomic spectra that we've been looking at that those have to be atomic lines. But since they're dropping down, they're absorbance. So we have the solar spectrum, and then we have some missing light. And that missing light is due to atoms that are absorbing that light in that light's path from the sun to our detector. So something between the sun's emission and our detector is absorbing this light, and it's really narrow, so we know it's atoms. And so we can look and compare it to experiments on Earth, and we can say that A and B, right here, these A and B lines, those are actually molecular lines. Those are oxygen O2 lines. And then we see some hydrogen lines. So C is a hydrogen line. It looks like F and G over here, these are hydrogen lines. So those are the three. We looked at them as emission lines of hydrogen, but this is showing that there must be some ground state hydrogen between us and the sun that is absorbing that light. And then we see sodium, which is here at D, this sodium doublet. And then we see that at E we have of iron. That's really weird, isn't it? I mean, oxygen is pretty straightforward, right? Oxygen is in our atmosphere. So we would expect to see oxygen. We have a lot of hydrogen in terms of water, so maybe water vapor is getting in our atmosphere and it's getting blown apart by some UV light or something. We have some hydrogen, so maybe the hydrogen is in our atmosphere. But sodium? How much sodium is in our atmosphere? None. Iron? Do we have a lot of iron atoms floating around in our atmosphere? No. So where do you think those elements are? Somehow, either they're in space or they're in the solar spectrum. So think of, you know how the sun works? So all the atoms, gravity is a long range force. It's a weak force, but it's a long range force. And so given enough time, objects will typically, or will tend to move towards each other because of gravity. Okay. And so hydrogen, the most abundant element at the beginning of the universe, the hydrogen atoms got closer and closer together, formed hydrogen molecules. And then the ones that were in the middle couldn't escape as we got more and more hydrogen together, and they started banging into each other. Okay. And then as it got more and more dense, eventually the hydrogen molecules in the middle were getting compressed and compressed and compressed until they fused. And that generated an enormous amount of energy that couldn't escape because there was so much hydrogen around it. And so that increased the temperature of the hydrogen gas around it. And then the star is essentially lit. It starts to emit enormous amounts of light as it tries to get rid of this energy of fusion that's happening in its core. Okay, so this is how a star lights. It gets more and more dense with gravity, and then the collisions raise the temperature up to over 2 million degrees, and eventually the nuclei touch. And when the nuclei touch, two protons touch and they form a helium nucleus. And then you have a helium atom bouncing around in there. Okay, it's heavier, it's more dense, more hydrogen hits it, and maybe you make a lithium ion. And so then there's this fusion is the engine that's generated all of these heavy elements. Then you start fusing whole elements together. You get a calcium and a barium to fuse, and then they make the transuranic elements and so on. So we get the whole periodic table formed in the middle of that star from collisional fusion in incredibly hot temperatures. So we're to 6,500. That's just the temperature of the gas around the outer part of the sun. So we're getting light from that outer part. We're not really getting much light from the inner part of the sun. It doesn't escape. It's caught in there and it's getting absorbed by the other elements and so on. So it's also blowing off a lot of gas. You may have heard of the concept of solar wind. So this is molecules and atoms, mostly atoms, at the outer edge of the sun that have escape velocity or near escape velocity. So they get blown out of there because, let's say that reaction happens near the surface, it releases an enormous amount of energy and it blows this gas out off the surface of the sun. Yeah. And then that gas goes out into the atmosphere. And what does it do? Well, it emits energy and it reaches the ground state. So this atmosphere around the sun contains a lot of ground state atoms. And so the light going through that atmosphere is absorbed by sodium, ground state iron. And then when it comes to us, we see the dip in the light that's emitted from the sun. So we get all of the wavelengths of light off the surface of the sun, that hot gas. And then this cloud around the sun has cooled. And so we have ground state atoms that absorb. And we'll see oxygen absorbing, we'll see sodium and iron and so on, and hydrogen, a lot of hydrogen. And so that's why we see these Fraunhofer lines in our spectrum. And then we can look at, with different satellites and so on, we can analyze these galaxies far away with all kinds of different wavelengths of light. And, it's interesting in different wavelengths. So like here in the UV, this galaxy doesn't look like it has very many stars, okay? and then here in the middle, it looks like it has more stars. And then here in the infrared, you see that where we didn't see much out here like this, that's emitting in the infrared, or at least the light's appearing like it's in the infrared. And so we can put all of these different things together and create a composite image of this galaxy. So this has given us this standard cosmological model. Cosmology is the study of the beginning of the universe and the development of the universe, and we're out here. So we'll just pick a galaxy. We'll say we're in this arm here, this galaxy, that's the Milky Way. So we're like on a little map. You are here. Little Johnny's looking at the map and he goes, I don't understand how they always know where I'm at. Because every time you go, it knows where you are. Isn't that weird? Yeah. Anyway, so we've used our telescopes to look back in time, because when we're looking in distance and it takes time for light to travel, if we look at the sun, we're not seeing the sun right now. Does anybody know how long it takes light to travel from the sun? 8 minutes. So we're looking back in time when we look at the sun. If we look at a further star, we're looking back in time because that light left that star, say 1 million years ago, and it's taken 1 million years to get to us. So when we look at that star, we're looking back in time 1 million years. So that's a little weird to think about too. If we tried to find, we used years ago this cosmic background. We put up microwave satellites, and we also used some terrestrial satellites. It was interesting. As we were using microwave communication, there seemed to be static always on the line. So this is where we got this idea of a cosmic background, a microwave background radiation. And so, these microwave receivers for communication would always have this background static on. And they're like, what's going on? Even if we aimed them at the sky where there shouldn't be any microwave radiation coming, we could always see this background static or background radiation signal. So we decided to map the universe in the microwave, and that's where this afterglow, they call it, pattern showed up. So this is the microwave background. And so this is sort of this what they call the standard model of cosmology. So that's the sort of the most ancient light that we can detect, is this cosmic background radiation in the microwave region. Now, what happened here at inflation and what happened at the beginning is a big question mark. Now, they've got labeled on here quantum fluctuations, but that's just a guess. So we do not know scientifically what happened here at the beginning. Inflation is a confusing thing because it is much greater than c, much greater than the speed of light. So that breaks physics too. So we have at the beginning of the universe something that breaks physics. So we have no idea how that came about. So let's look at this idea of the expanding universe. We can see here from this. Now we've taken the three-dimensional universe and we've reduced it to 2 dimensions. And so if we could think about our universe being a disk here, so each one of these disks would be a disk in time. So this last disk would be the disk that we're living in time. And you could kind of think of it as the surface of a balloon. And so if you have 2 dots on the surface of the balloon and you put more air in the balloon, they're going to get further apart in all directions. So the surface of the balloon is an idea of thinking about space, but we're only able to picture in our minds 2 dimensions, and the expansion is the 3rd dimension, which is time. So it's hard to convince. I mean, it's hard to conceive of sort of this 4-dimensional expansion. So our 3 space dimensions are expanding with time. And so you could run this backwards, and you see it's not a linear expansion. And also, what happens when we expand the universe? So light is being emitted. I'll just draw this light wave. And let's say I was running forward towards that light wave. It would appear to me to be going at a higher frequency because it's coming past me very quickly and I'm moving towards it. And so I experience the waves in troughs much faster. So it would be a blue shift. But if I'm moving away from it, it's still faster than I am. But it goes past me and it appears to be going slower. So a slower frequency would be a red shift. And so this is the evidence for an expanding universe. We see a cosmological red shift as we look around the universe. So this sodium line is what we're going to use to track it because it's right in the middle of the visible regions, very strong line, very well known. And so if we look at a star, so this might be the spectrum of our sun with that sodium line missing, that dark line. And then we look at a star that's pretty far away, we see all of those Fraunhofer lines have shifted towards the red. So that's what we mean by a red shift. Okay, so if we have this sodium line at 589, that's that singlet S0 to the doublet P 1/2 and the doublet P 3/2. We did the term symbols for those. Those are the two spectral lines that we get. These are the Earth. See the lambda E? That's for Earth. These are the Earth wavelengths. And then we look at that star and we see that it's at 592 or 591.8. So the observed wavelength of that star, we know it's the sodium line because it has the same intensity pattern and it's been shifted. And we look in the yellow region and there's no line there. So this is the red shifted sodium line. So we can calculate this Z factor. So that's the difference in the observed from the Earth wavelength divided by the Earth wavelength. Sort of a percent shift, if you want to think of it that way. So it's not a lot in this case. It's, under 1%. So it's 0.4749% shift. So, but still very easy to measure. And this will give us our velocity of expansion. So if we take that percent shift and multiply by the speed of light, then that star is moving away from us, or we're moving away from the star, or mutually, like on the surface of a balloon, everything's moving away from everything else. We're moving away at 1,400 kilometers per second. We're moving pretty fast. Or in relative to that star, 1,400 kilometers per second. So even if you think you're still, you're cruising, okay, through the universe. Now, Hubble's law was able to take this, we needed a scale. So we've got this velocity change here, but how does that tell us the distance in terms of how far we are from these stars? So have you ever thought about how we detect distance with just our eyes? We actually have two detectors here, and they give us what's called parallax. And the brain can't deal with two images. And so in order to get the two images that my eyes are seeing to make sense, the brain interprets depth and gives us that Z component. Okay. It's like when I'm looking, like comparing this faucet to the corner of that desk, if I close my right eye, I can see the corner of the desk on the right side of that faucet. But if I close my left eye, I can't. And so my brain is confused. Can I see the corner or not? Well, I can if I realize that the faucet is closer to me than the desk. And then it makes sense, and I get 3D vision. So we do this in 3D movies all the time too. So in a 3D movie, you have glasses that you put on and they're polarized. So one eye is polarized. Typically they do diagonal polarization. So it'll be like this. So the film that they're showing on the big screen shows one image polarized like this, and my right eye gets it. And then it shows the next frame polarized like this, and my left eye gets it. That's why when you put on the polarized glasses, the light drops by 50%. Because you're only seeing half the light. Half of the polarization is getting into this eye, and the other half of the polarization is getting into that eye, and you're throwing away half the light in a non-polarized source. And so the projectors are talking to your right eye than your left eye, and they're giving you two different shifted images, and your brain is interpreting that as depth. And so that's why you get why a 3D movie is fun. So that's called parallax. We see it all the time, and now you're going to be doing that, and you're looking in the room, and you're going to quote in one eye and so on. We can do this with the universe too. So how can we get two eyes to look at the universe? And the farther apart your eyes, the better you are at parallax. Okay, the better your depth of vision. So what can we do on Earth to get a parallax image of the universe with our telescopes? Okay, so like if we've had two telescopes on two different continents that were on the opposite side of the Earth, so that would be good. So but it's limited, so they would be able to look, because they got to see the same image. But that's okay. It would work. They would get a good view of like two wheels. So let's say we had one in like China and the U.S. I think they're pretty far, like on the opposite sides, maybe some part over there, and we would be able to look at images this way, right? Like two wheels. We could see the universe looking north, like you said, and looking south, and whatever. As long as we could get a same vision of the universe, we could do that parallax. So opposite sides of the Earth. What if we just had one telescope on Earth? Okay. And we did spring and fall. So we take an image in the spring, and then we wait until the Earth goes all the way around the sun, and we're in the fall, and we take an image of that same spot in the universe. Now our eyes are as far apart as the whole transit of the Earth, the solar system, at least the Earth's orbit. That's cool. Okay. And so we've done this. And so this is what we mean by the near distances match orbital parallax. So we've taken main group stars like our own, and we said, how bright are they? Notice we have an iron line. Iron is right there in the middle of the periodic table. It is one of the most stable elements. So stars will do fusion until they get to iron, okay? And the higher elements are not as stable as iron. So iron is like a thing that collects in stars that will tell you somewhat the age of that star, okay? And we can track iron content and brightness, and we can also classify stars by their iron content. So we know where we can find stars like ours, and if we have a star like ours, it probably is the same or similar brightness as ours. So we can look in these images and say, okay, this star has a similar iron content to ours, similar spectrum to ours. It's probably just as bright as ours, but it looks really dim. Why would it look dim? It's because it's farther away. So we could track brightness with distance, and then with our parallax image, we could say, wow, in this image, that star's over here to the right. In this image, that star's over here to the left. So it must be closer to us or further away. And so we were able to match brightness with distance and parallax with distance. So we could map the Milky Way and adjacent galaxies using parallax and brightness. And we got this plot. So this is an amazing plot. Okay. So we have over here the red shift, which we're able to measure with our atomic spectroscopy. And then we're able to measure this distance here with the brightness and the parallax, and we get a linear relationship. Now, it's not the R squared that we're used to in physical chemistry, okay, with the 0.9999 R squared, but it's pretty good, okay. Now, there's a little cluster in the middle, and remember, we're measuring redshift, and so some of these have a higher redshift than these down here. These are stars all in the same galaxy, okay? And so that galaxy is rotating, and so some stars are coming towards us, and some stars are going away from us, and it's the rotating of the galaxy that's giving an extra redshift for the ones that are going away from us, and the others are coming towards us, but they're not redshifted as much as we expect because they're spinning. So as they're spinning, the ones that are spinning towards us have less redshift, and the ones that are spinning away from us have more redshift. And so we see that little cluster in the middle, and so we've corrected for that. We've come up with this Hubble's law. Now we're dealing with enormous distances. So these are light years. So we've used a new unit instead of the speed of light or distance in kilometers. We're using the distance that light travels in a year. And these are megaparsecs, which is a million parsecs, which a parsec is 3.26 light years. So this is 3 million light years is a megaparsec. And so this is the Hubble constant. You see, it's not, we've got basically 2 sig figs, okay, but it's still able to calculate the velocity versus distance. And so we can take this velocity that we just calculated, which was c times z, and divide by that Hubble constant, and we could get the distance of the star. So let's practice. Okay, so what if we have this star here that's 20 megaparsecs away? Okay, where would that observed sodium wavelength be from that star? Okay, so we could just we just want to solve for this L0 or LO, the observed wavelength. We've got distance, 20 megaparsecs. We've got the Hubble constant. We've got the speed of light, and we've got lambda e here. And so it'd be 592.4 nanometers. And so then when did that light leave that star 20 megaparsecs away? Okay, 20 megaparsecs is 20 times a megaparsec, so 65 million years ago. So how many meters is that? Well, we can go through. This is how far light travels in a year. Okay, 365 days in a year, 24 hours a day, 3,600 seconds per hour, and then we have the speed of light. So it's almost a mole of meters. Okay, so that's kind of an interesting fact too. If you were traveling at the speed of light and you wanted to go a mole of meters, it would take you 65 million years. The mole is a big number. Okay. And so this is just, I don't know, it kind of breaks my brain to just to be able to think that here we are sitting in our Milky Way, and we're looking at a universe or a star that's 65 million years away, and we can detect the distance by using the red-shifted sodium line. We know it's sodium because it has the same intensity pattern that sodium has. In that spectrum, there is no sodium line. It matches all of the lines, but it's shifted to the red. It's red shifted because we're moving away from these stars and galaxies at an enormous rate, 1,400 kilometers per second. Okay, and we put up space telescopes like the Hubble telescope and now the James Webb telescope, and we've looked back, like you pick a dark patch of the sky where there's no stars and you aim these telescopes there and let it collect light for days and days and days, and all of a sudden you see like ancient galaxies emerge where galaxies are really close together. So back in this area here, the galaxies were close together, and you see things that are really crazy, like this galaxy being so close to this galaxy that they're stealing stars from each other. And so look at some of these images where galaxies are eating other galaxies and so on. It's just really crazy. I used to love, using a telescope. I had one as a kid. The high school let me take the school telescope home over Christmas break. I was pretty excited about that. I could see the moons of Jupiter and the rings of Saturn, but I couldn't see anything like this. And so, although it was exciting to see the Hubble telescope go up and see these images that are amazing, it made me want to throw rocks at my regular old telescope. So all I could see was a white dot. You look up there, you see a bright dot. Okay, that's a star. Maybe you look at a nebula and it just looks like a smudge. Okay, but now if this interests you at all, and you later on when you get a job and you have some extra cash, you look at these C-star telescopes because they're computer controlled. and they follow the stars and can collect light for hours. So you can set it out at night on a clear sky, and you can dial in, like it's the star chart and everything's all built into the app. And you say, okay, go look at the Orion Nebula or whatever, and it'll follow that thing all night long and collect light for an hour or two, and you get Hubble-like photographs. It's absolutely amazing. Yeah. So anyway, that's my recommendation. They're really cool. And so this is an excellent video if you want to go through it. This is by physicist Michael. I've followed a lot of his stuff as he was explaining this, so that's where this data came from. And so let's think about this idea of 65 million years ago and further. I mean, we look back at this, we can look further and further back and see, from this inflation, about 13.7 billion years of the development of the universe. Using that Hubble constant, we can look further back in time and look at the redshift of all of these different stars, and it just marches all the way further back. Okay. So what confidence do we have that physics is the same 65 million years ago or today? And this is how it ties into our atomic spectroscopy. Spin orbit coupling. So what we did for sodium and coming up with that doublet P 3/2 and the doublet P 1/2, those term symbols for those levels, we see the same thing in these ancient star spectra. So this change in energy between that doublet is related to this Bohr magneton, which is a property of an electron. And it's the thing that converts the magnetic field, B, this magnetic field, that's measured in Tesla. So in this case, T is not temperature. T is the magnetic field in Tesla. Did y'all know that was the unit of magnetic field? Okay, good. Okay, so the magnetic field strength in Tesla converted to energy, that's the Bohr magneton. So that's a property of the electron. We see the same spin orbit coupling with all of these stars going back for 13 billion years. So there's not a different kind of physics, at least from the inflation to present day. Now, what happened at inflation, we don't know. That's still a mystery, okay? And what caused the Big Bang to start, we don't know. Now, quantum fluctuation, you hear that a lot. So what is a quantum fluctuation? Well, we will see this process of what they think is a spontaneous generation. I'll just draw a little poof here, okay? And an electron come out and an anti-electron. Did you hear me? What is an anti-electron? Okay, it's antimatter. So we'll have a matter-antimatter pair. Okay, and if you take my next semester, when we get to the very end, we start talking about nuclear chemistry. We start talking about all the different nuclear processes, and annihilation is one of the processes that we will study. But we use this now to do medical imaging. We have elements like boron, oh gosh, I forget, is it boron 10? No, it's carbon 10 that becomes a boron 10. So we have a carbon isotope that's generated inside a nuclear reactor that produces carbon 10, which gives off a positron when it decays. So it spits out a positive electron, an antimatter electron. And so as soon as it gets out of that carbon nucleus, it finds an electron, either on that carbon atom or somewhere nearby, but it doesn't go far. Because think about all the electrons in our regular atoms. Those are all normal electrons, and here comes a positive electron. And when they hit, they annihilate and spit out 2 gamma rays. This is the reverse of that process. This is the result of the collision of 2 gamma rays. So 2 gamma rays come in and hit, and they create this positron-electron pair that then annihilates and spits out 2 gamma rays. So from our perspective, did the matter-antimatter thing actually exist? Well, maybe it's detectable, but what macroscopically is happening is light is actually colliding. So two gamma rays are coming along, very improbable, okay, but they hit, there's a little matter antimatter thing, and then two gamma rays come off. It's like scattering, okay? So these two gamma rays hit and they scatter off of each other, but when they hit, they generate this matter antimatter pair that then annihilates again, and then they spit out the gamma rays. So it really looks like two gamma rays just bounced off each other. So this is what they mean by a quantum fluctuation. And the physicists are happy to say that this is something coming from nothing. So they're restricting their description of something as something that has mass, because these have mass. And the gamma rays don't have mass. You say, wait, how does matter how does mass disappear? Well, remember that equation, E equals mc squared. So energy and mass are interconvertible. So we had the energy of the gamma rays producing mass, and then the mass goes away and gives us back energy. This is very cool stuff, okay? They're saying that this is something coming from nothing, but I see two gamma rays, I don't see nothing. Okay, so for that to start the universe, you had to have light. So this is not nothing. So I don't think quantum fluctuations explains the very beginning, because you had to have light to get the quantum fluctuations. So it's still a mystery, but I don't think quantum fluctuations is the thing that answers it. Okay, so the splitting and relative intensities match those in the NIST atomic spectral database, meaning they haven't changed in the spectra of ancient stars. And I just thought it would be fun to insert this here in our course, because we just finished talking about term symbols, the sodium atom, the singlet S0 state going to the doublet P, 1/2 and 3/2, and that's the two lines that we're using to track the stars in stellar spectroscopy, which is pretty cool. So this really isn't anything on the test. This is just a little side trip, a side quest, a big side quest out into the universe, and then next time we'll get back into the material for the course. So hope you'll have a good day.